What about the strong electrolyte solutions? Strong electrolytes give larger effects in these colligative properties because they separate into ions. There's more particles. The Van 't Hoff factor is given the symbol I, is the ratio of moles of particles to moles of formula units dissolved. So the moles of particles in solution divided by the moles of formula units dissolved. The reason that we need to use a Van 't Hoff factor is because some of the ions will pair in solution, and so we can't just predict what the concentrations are going to be by looking at the formulas. Now, if we have calcium chloride, CaCl2, we would expect 3 moles of particles for every mole of solute dissolved, but it's not actually quite that. So the Van 't Hoff factor is sort of a fudge factor. So what happens is that the pairs, the ions can actually pair up in solution even though they are in solution. And when they pair up like that, they act like one particle. And so that reduces the effect on the colligative properties. So here are some of the Van 't Hoff factors for 0.05 molal concentrations. And for a non-electrolyte, the Van 't Hoff factor isn't needed. It would just be 1, and it's expected to be 1. Sodium chloride, we would expect there to be 2 moles, but it's actually 1.9. Potassium sulfate, we would expect a factor of 3. It's actually 2.6. So you just need to look up the factor and apply it. So this factor, I, just gets thrown into all of these equations for a strong electrolyte. So calculate the freezing point of an aqueous 0.1 molal iron chloride, iron 3 chloride solution using a Van 't Hoff factor of 3.2. So we want the freezing point, we're going to need the freezing point constant, which I think was 1.86 for water. The freezing point constant, 1.86, that was degrees Celsius per molal. We've got a Van 't Hoff factor of 3.2. What would we expect for iron 3 chloride? How many moles of ions per mole of solute? 4, right? Because we've got 3 chlorides and 1 iron, there should be 4. So the freezing point depression, the change in the freezing point, is equal to the Van 't Hoff factor times the molality times the freezing point depression constant. So we've got 3.2 times the molality, 0.10, times the factor, 1.86. No, I'm getting smaller and smaller, sorry, degrees Celsius per molal. Our units cancel out. 3.2 times 0.1 times 1.86. So the change in the freezing point is 0.595 degrees Celsius. And it's going to have a 2 safe fates. Normal freezing point for water is what? 0. I feel like I'm lecturing to myself. Nobody's saying anything. Some people are reading books. It's very rude. So the freezing point of the solution with 2 safe fates is going to be 0.60, negative 0.60 degrees Celsius. Any questions? So strong electrolytes also are going to have a larger effect on vapor pressure lowering. And when we're calculating the vapor pressure with strong electrolyte solutions, we have to account for that dissociation when we're calculating the mole fraction. So it's not going to come in as a Van 't Hoff factor, but it's going to come into the mole fraction. Okay, so calculate the vapor pressure of a solution containing an ionic solute. So the solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees is 25.7. The vapor pressure of pure water at that temperature is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. So this isn't calculating the vapor pressure lowering, this is calculating the molarity, or the number of moles of solute, from the vapor pressure difference. Well, the vapor pressure of the solution is going to equal the mole fraction of the solvent times the vapor pressure of the pure solvent. That was way back at the beginning of today's lecture. This time, we don't know what the mole fraction is, but we know the partial pressure of the pure solvent and of the solution. So we can calculate the mole fraction of water is going to be equal to the partial pressure of the solution divided by the vapor pressure of pure water. So the vapor pressure of the solution is 25.7 torr. And the vapor pressure of water is 31.8 torr. So the mole fraction of water is 0.80818, 3 sig figs. That equals moles of water divided by moles of water plus moles of, I'll just say ions, shorter than particles. It's not the moles of sodium chloride, because the sodium chloride dissolves and separates into ions, right? So this solution has 0.115 moles of water. So we can put 115 moles of water in here for N of H2O, and then we can solve for the number of ions. I'm going to rearrange the equation first because that's what I prefer to do. So NH2O plus the number of ions is equal to the moles of H2O divided by the mole fraction. And then to get the number of ions by itself, I'm going to take that quantity and subtract the number of moles of water. So the moles of ions is 0.115 moles of water divided by 0.80818 minus 0.115. Point 115 divided by 0.80818 equals, and then subtract 0.115. So I get 0.0 27 0.295 moles of ions. If I have that many moles of ions, how many moles of sodium chloride do I have? I need to divide by 2, right? Each unit of sodium chloride that dissolves produces 2 ions. So I have twice as many ions as I do moles of sodium chloride. So I take this and divide by 2, and that is my number of moles of sodium chloride. Any questions? Yeah. Oh, yeah. Subtraction. Here I'm subtracting. So I should only have to the 3rd decimal place, so the 7. Thank you.
I'll change your suffix.
Yeah. So we change this. And this will be right here, and 0.014 moles. That's better. Thank you. Any other questions? Colligative properties are very important in medicine because when you administer IV fluids to someone, you don't want that solution to be drawing water out of the cells in their body. You also don't want it to be pushing water into the cells. A hyperosmotic solution or a hypertonic solution has greater osmotic pressure than bodily fluids. And that will draw water out of the cells and cause them to shrivel up. Here's, I believe this is an electron micrograph, picture of normal red blood cells. They're kind of donut-shaped. If the solution that they are in is higher in concentration of solutes than inside the cells, it will draw water out and cause them to shrivel up. That's not a good situation. If we have a hypoosmotic or hypotonic solution where the concentration is less, that will force liquid into the cells and cause them to swell, and they may eventually burst. Also not good. So hypoosmotic or hypotonic, lower osmotic pressure, lower concentration causes them to burst. Isoosmotic is what you want, isotonic. Those have osmotic pressures that match those of bodily fluids, and really, really important for intravenous solutions. So what's known as isotonic saline is 0.9% or 0.9 grams sodium chloride per 100 milliliters of solution. That matches the osmotic pressure of the cells. A common unit used in medicine is percent mass to volume. So mass of solute to volume of solution.